Hi, and we're still on quantitative chemistry, almost at the end of that section, but the purpose of this lesson is a summary, really, to bring a lot of the science we've been learning recently together. So going through this a stage at a time and checking your understanding. Hopefully by the end of this you'll either think to yourself, right, I know most of that, or I know all of that, or these are a few bits that I need to cover before I do any assessments in this. So the first thing I'm asking you to do is to draw the electron structure of magnesium. It has an atomic number of 12 and an atomic mass of 24. So, remembering how many go in each shell, etc., there's going to be lots of pause points in this where I just say pause now, so you have a go at that yourself, and then check if it's in line with what I'm doing. So pause now, and now you're back. So what should you have done? You should have said Mg. You should have drawn the first shell, and hopefully you've put 2 in there, because this is the atomic number. This is the key one over here, the 12. 12 protons, so 12 electrons. We put 2 in here. Then we put on the next shell. And hopefully you remembered that 8 can fit in there. And we've got enough to fill that up. 1, 2, 3, 4, 5, 6, 7, 8. So now we've got 10. And there's 2 left on the outside shell. So it's got 3 electron shells, the valency of 2, because there's 2 on the outside shell here. And if you've got that, brilliant. Now can you pause and can you fill in? Now what you're doing in your notes is you're writing out these bits as well. So actually do enough detail with it so you know what you're doing. So you can write down, in magnesium there are so many protons, there are so many electrons, there are so many neutrons. So pause and have a quick go at that. Okay, so I'm hoping that you wrote 12 here because that is the atomic number, the number of protons. Then you would have thought to yourself, if it's got 12 positives, it must have 12 negatives. And then for this last number, the number of neutrons, the mass is 24, take away the 12 protons, and that leaves me this time with the same number, 12 neutrons. So you would have put a 12 in here. And then this last bit, what does magnesium need to do to have a full shell? Because that's the whole purpose of reacting. That's why chemicals react and bond with each other, to get that full shell. So, pause, have a think, look at it, have a guess. Let's see if you're right in a second. Right, are you right? It needs to lose or give away or transfer 2 electrons from its outside shell. So, hopefully by now you're feeling pretty confident. I'm going to take magnesium a bit further. First of all, we're going to draw the magnesium after it has reacted and lost its 2 outside electrons. So this time, all I'm going to do is I'm going to draw the 2 on the first shell, and I'm going to draw the 8 we had on the next shell. 1, 2, 3, 3, 4, 5, 6, 7, 8. Now I'm not going to draw the other shell in because it's lost to those 2. Right, pause. What do you need to do to this diagram? Okay, I'm hoping this is what you've done. What we do is we draw a square bracket around that structure. And now it's still got its 12 protons, but it's only got 10 electrons. So overall, it has a charge that is positive by 2. So that's just a bit of thinking over here. On the diagram, it looks like this, plus 2. So, Mg plus 2. You should have got a mark for drawing a square bracket, a mark for saying it's positive, and a further mark for saying it's positive by 2. So don't mark yourself wrong if you only got 1 or 2 of those. Next question I'd like you to consider on magnesium is, how are the magnesium atoms bonded together? Okay, now what I'm hoping you're thinking of here is it's just a piece of metal, and in a metal the atoms We're in a regular structure, and there's a small positive nucleus. And then what do they do to their outside electrons? And that's the main difference in metals. Metals let the electrons go free. They share them between them. And so hopefully in your answer, what you've got is, because the question says, how are the atoms bonded together? Well, we have two main points to make. One is positive metal ions held by a sea of delocalized electrons. So they're held in place by a sea of delocalized electrons. Right, moving on. But what if magnesium didn't stay as a piece? What if it reacted with a non-metal, like oxygen? So the thinking behind this before you start is, well, this one had to lose two. And when it loses, like all metals, it becomes positive. But oxygen down here only had 6 on the outside shell, 2 on the first shell, then 6. So this needed to gain 2. And if it needed to gain 2, it became a negative ion. Right, pause and see if you can work out about the bonding it will have. Okay, what I hope you've put is, first of all, ionic bond, which is an electrostatic attraction between positive and negative ions. An electrostatic attraction between positive and negative ions. Okay, what does that mean for the structure? And if you remember, those attractions were in all directions, so we ended up, just draw a small section of it here, and remember, I can't draw in 3 dimensions, but in earlier lessons when we looked at structures and bonding, it's a 3-dimensional structure. Made a mistake there, didn't I? Look at that. Just goes to show. Get rid of that, get rid of that. So alternating positive and negatives, held together really strongly by these electrostatic attractions. Right, what structure is that? Pause, see if you can remember, see if you can have a go, have a guess, because you can always correct it as we go through it. Okay, this structure is called a giant crystal lattice. You could say more. You could say about bonds and attractions in all directions. You might have even gone on to say some of the properties. You could have said it's a solid. You could have said it has, because the properties, it's a solid, it has a high melting point, because you need a lot of energy to break those bonds to turn it into a liquid. And now, more recently, we've got to equations. Now, if I drew this, what I'm actually saying in this equation at the moment is 1 magnesium atom plus an oxygen bonded covalently to an oxygen, because they're non-metal sharing, can react together to form a positive Mg and negative O like that. And you can immediately see there's a problem here. So, see if you can have a go at balancing this equation. So draw it out again, draw this version out first, like that. Then, what you're going to change about it to try and balance it, that one in the box. So, pause, try it yourself, even if you try it in pencil, so you don't mess up your work, that's fine. Okay, so first of all, I would think I have to make 2 of these because I need to have 2 oxygens this side, so I'm going to put another MgO here. So that way now, my oxygens, I've got 2 this side and 1, 2 this side. That's fine. But because I've got 2 magnesiums this side, I now need to go back and put a 2 here. So to balance that equation, all you had to add on was a 2 this side for the magnesium and a 2 this side for the whole of magnesium oxide. If that's not something that's coming easy to you yet, go back to the lesson about that where you can practice them. And then even more recently, we started adding masses. So we looked at the mass numbers from the periodic table. So you've got 24 here for magnesium. You've got 16 here for oxygen because it's rounded to the nearest. So that's 16. So what does that mean? Well, what does this say? 2 magnesiums, 2 24s. Oh wow, that's hard. That says 48. Plus, 2 oxygens, 2 lots of 16 is 32. And the way to work out whether you've got it right is, this says 24 plus 16 for the masses, add them together, and then times the whole thing by 2, because it's 2 here. 24 and 16 is 40. 2 times 40 is 80. Let's put that down there. So, 48 and 32 added together do make 80. Bing! I know it's balanced correctly, and there's my masses. And then the last bit of what we've been doing recently is we now have these. So we had that mass a minute ago, 48 plus 32 make 80. If we're looking at moles, that's what this is telling us, 2 moles, not 1 mole, if we want to deal with real quantities of chemicals. So that could be, instead of 2 atoms, we could have 2 moles there, so that could be 2 moles, and that would be, there's a number 1 here, so 1 mole. And there's a 2 moles. So we can now say, well, if you take 2 moles of magnesium, they would react with 1 mole of oxygen and form 2 moles here. And if we had that, if we actually do this equation, remember MR, the relative formula mass, is in atomic units. The beauty of moles is moles turns atomic units into grams. So real scientists can use them in everyday life. So 48 grams of magnesium, if I burnt that and it all burnt perfectly, I would end up with 32 grams of oxygen joining with it from the air. And what I was left with at the end, my magnesium oxide, I would have 80 grams left. Now, just going to say one final thing about that. There's lots of reasons. Some of this magnesium might not react. Some might escape as a bit of smoke. Some might be left in a container. So we very rarely get exactly the right answer if you do the practical. We might end up getting something like 75 grams. And we've sort of lost 5 grams along the way by being a bit sloppy. But the more accurate you are doing it, the closer you will get to that. So that's the true value. Although it's not always in practical science the value you would get. Okay. What I'm hoping now is that this has been useful in summing up and bringing together lots of ideas from recent lessons, and that you've got it all in one place now as a bit of a summary page just based around magnesium and oxygen. And the same applies for loads of other atoms. Okay, thank you for listening.